Okay, for online students, have you finished scanning the QR code? Okay. So, okay. Uh, about the log. Um, Before I start the course, um, today is 20 October. Um, I'm planning to have a quiz for basic math. Quiz 1 basic math. This is on um, October 27th. Hmm? I want to just make sure that we agree this 27th. For online students, so you are finishing your quarantine 27 October. Okay. Okay, so everyone will come to the class. Okay, 27 for online student. Okay. Okay, so next week will be quiz. Okay, so all chapters from I think 1, 3, right? One is the numbers functions. Two is the let's say quadratic polynomial functions, and three is the exponent and log. And I think our courses start at 9:10, but our quiz will be start on I think 9:15. Okay, so you only have around 45 minutes to solve the questions, so up until 10. Okay. Okay, so three chapters: numbers, functions, quadratic polynomial, exponential log. Okay, please come before 9:50. Okay. Okay, now let's start our course. Um, let's start with this question. Okay. At the very beginning of our course, I said that logarithm is the inverse of the exponent. Okay. If you have the functions um, 2 with the power of 3 with the power of x. Okay. By the way, this is not the same as different. Okay, different. So if I have 3 or maybe 2, 2, 2, 2, this is also different than this. It's not the same. Okay. Okay. This is just for your information. Okay. So this is my function. I need to find the inverse. Okay. Um, Anyone remember how to find the inverse? Okay. For example, I will write some functions to help you. If I have the x squared, okay, or let me write in y is x squared. To find the inverse, okay, you need to switch the domain and range, basically, right? So you switch the y and x. So solve for x. So x will be square root of y, okay? And by doing so, I'm basically changing the domain and range. So I can write the f inverse of x is square root of x, okay? Got the logic? I won't repeat again, okay? So do the same thing with this one. So aim to switch this exponent with this y. Okay. Any idea how we can solve it? Hmm? Hmm. Can you write it? How? Is it try make some number x and y? Is it true or not? Okay. Okay. Any idea how to solve this one to find the inverse? Yes. 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 So basically, if you add log, let me write here. Let me just write adding log, adding log. By adding log, I can make this 3 with the power of x to the front. Okay. Or I can just use the first property of logarithm, which is log 2 of y, the result, is equal. Okay. Okay. This will, if you prefer just adding log, log, and solve, it's the same thing. It's the same thing here. Let me just erase this part. So if I'm write this log y and then 3x log 2, it will be, and from this part we can have log, same thing, okay? So, but you can always use the the first property of logarithm. This is the result. This is the base. This is the power. Okay. So log base 2 of the results y is equal 3 with the power of x. Okay. And then after we get this, what we can do, we still have the power. Then log one more time. Okay. So I can write this as just log like this. And it will be x log 3 log 2 y. And we solve for x with the y inside. Okay. We solve for x, and this x will be the f inverse. Okay. Let me just give you the answer. Okay. So by just using the property, you have a, b, c, log a, c is b. Using this property, and you get this one. And then the same idea, okay. Same idea happening here. And then we can solve the x for the f inverse. So let me write this is the result, right? This is the power. This is the base. So same thing happened. This is the base. This is the result, and this is the power. Okay. So that's also a reminder how to find the inverse. Okay. From any functions, not any functions. I think only one-to-one functions. Okay, any questions? I will go for a little bit for some modeling in exponent and log, basically the exponent. Let me go to the exponential growth. Okay, because I think you also having this in calculus. Let's say it's doubling. Okay, so let me write the general expressions. Because it's doubling, it start with a base of 2. This is the size, total size. This is initial size. T is for time. A is for doubling time. And I will just give you the example. Okay, so how to use it. So under ideal condition, let's say bacteria doubles every, for example, 3 hours. Initially, there are 1,000 bacteria. Find the model. after t hours. So it's general model for this bacteria. And how many bacteria after 15 hours? And then the third question is, after how many hours bacteria reach reach 100,000? So these three questions is typical questions in any exponential growth modeling. Okay. So usually they will ask the model, the equations, what we can models after the activity, and then asking the total size after some hours, some time, and then you will be asked the time when it reached some numbers. Okay, these three typical questions. Okay, let's just move to how to solve it. Okay. So models, I will write. Our initial will be 1,000 based on the informations, and because it's doubles, so it's doubling. So we are using base of 2, okay, and then t over 3. So this is our model. We just plug in all the information we receive, and after 15 hours, so t become 15, okay, and then we need to find how many the bacteria. So this is, or I can write this as 32,000. So 32,000 bacteria. Okay. And then the third question is, if the bacteria reach 100,000, how many hours? Okay, so we are looking for the t. So it's 100 to, and to solve this, we can use the log. Let me just use log 100 and then equal log to log 100 is just 2, and let me divide by log 2 at t over 3, and then t will be 6 divided by log 2. Okay. If you are solving this in the exam, just stop here. Do not compute log. Do not use calculator. I forbid it. Okay. So just stop here, and that will be perfect. So that's the case if we are assuming that the bacteria based on the models here is doubling. Okay. So doubling means the base is 2. So if sometimes you read, oh, maybe it's triple, maybe the base of 3. So doubling, tripling. Okay. But our natural growth, or our relative growth rate, is based on Euler number. Okay. Hmm? What do you mean? Uh, no, it's just a common typical questions in modeling for exponential. So usually it's just asking the models, asking the how many bacteria after some time, and then how many time the bacteria needs to reach some number. Usually this 3. Okay, usually. Okay, that's the doubling. But for the relative or natural growth rate, we are using the, I think this expression will be also mentioning in calculus, okay? But with the little bit different, but the same concept. So again, this is the initial. This is time. And whenever you see any constant besides the time, for example, in calculus, you may see k, right? So if you see this r here, this is actually growth rate. Okay? So the population will be based on that growth rate. Okay? Do you know why? If you differentiate this, you're calculating the rate of change of the population, right? So if you differentiate E, it will go here, right? The R. If you make the T as your variable, R will go to the front, and you will multiply by another E, right? Okay, because it's when you differentiate E, you will get another E, right? So that's why it's really perfect for explaining how populations grow, okay? Because it can be multiplied. Okay? So that's the first case. The example is pretty similar from before. The difference is just the expression, and we are using the base of E, okay? The base of E. So why it's called relative or natural? Because with the base of E, practically we can predict how nature's works, how nature's population works. Okay? Okay. Another thing is the radioactive. Okay. Radioactive decay. Uh, Usually it's uh, we can write as m. It's from the mass, because what the decay really means is you have some radioactive materials with some mass, right? And the materials, they radiate some radiations, and the material itself getting reduced. Okay, so what we are talking about here, the decay, is when the materials itself losing its weight, losing its mass. Okay. Let's just write with 2 first. Okay, this is time, this is half-life, the age. Okay. This is initial mass. Notice you can see that this is negative, okay, meaning it's going backwards. It's reducing over the time. Okay, and then what is half-life? Anyone know? Half-life. Yes, correct. So half-life is when the your mass, okay, is initial divided by 2. Okay? It's half the initial mass. Okay, so I will write here mass is half. Okay, so it's a time when mass is half. Okay, okay, and then um, the relative decay is, okay, this is relative decay. And let's try to look up the half-life. Okay, Half-life is when the m is equal mo divided by 2. Let's divide this. Let's change the m into the um, mo divided by 2. Let's say this is the h, okay, because my mass already half. Okay, so this is my h here. I want to know what is the relations between this r and h. Okay. So this cancel, and I will get the ln half, or let me write step by step. So this is half is equal e, okay, and okay, by ln, I'm removing the e, and I can write r is basically ln half is negative ln 2. So it will be ln 2 divided h. Okay. Okay. So what does it mean by r? So meaning this is the relative growth. Let's say just growth rate. Okay. But it's in decay. Okay. So it's not growing. It's reducing. So I will use this as minus. Yeah, yeah, decay rate. In this case, decay rate. Yeah, you can say decay. This is just to make sure that well, when we are talking about r, the same r as the growth rate, it's actually the growth rate, but it's like backwards. Yeah, yeah, you can say also decay. Okay, so growth rate, decay, one more. Okay, it's called the Newton's law of cooling. So it's related to physics. So cooling means the temperature change from the higher temperature and cooler. Okay, uh, so the temperature will be equal to temperature of surroundings, and this is initial temperature, the d. Um, this is just a constant. You can say that also growth. Fine. This is time, constant growth. Okay. So notice that this is also having a negative because it's cooling, so the temperature should be lower. Okay. And I think practically all these examples, okay, as long as you understand the questions and how you are solving the problems, should be not really that difficult. And the problem is in calculus, okay, you are involving most of these examples with the rate of change. So you differentiate. Okay? But here you are just looking at the models. And by that models, you are trying to just solving the problems. Okay? But in calculus, you have the models. And sometimes you need to differentiate and see what is really happening, okay, in the rate of change. Okay. Okay, that's just like a really short sections about the modeling with the exponent. Okay, let's go back to our log because I think one or two examples I need to show. Let's go here. mm, Okay, this is the log equations example. Okay, I will just give you the example on how to deal with it. Okay, can you try for a couple minutes? Okay, what's the first one? Yeah, the x. Yeah, all is the solve for x. What's number one? Hmm? And then is there any other answer? Why? Why not the second one? Okay, okay. I think number one is not complete. The answer is not complete. Yeah, come on. Why you are asking? Do you have doubt? Uh, yes. And why are you not sure? Because negative part? Okay. If x is negative, that's impossible. But this is, okay. Yeah, it can be. Okay. If x is negative and you put that x, it would be impossible because it's out of the domain, right? Yeah, but uh, there's another answer. There's two answer, right? So this is the we are just making this log goes to the front, okay? And we can make this log x and log x, right? And we can just make log x and then squared is 49. Let's just square root both of this, okay? So we'll have log x is equal plus minus 7. I can write this, right? Because it's the log itself that minus, not the x. Okay? So log x is 7, log x is -7. And x here is 10. Okay. Okay, what is the second one? Careful. You have the squared. This is x squared. Okay. This is log x and then squared. Different. Okay. But you can still can solve this. Yeah. But there's another answer also. It's still incomplete. So remember every like you having log and then squared, at least you will have two answers. Okay. This is also similar cases. Yes. Yeah, correct 1 and 100, correct. Okay, so I can move 2 from the x squared. Okay, so move 2 here. So it's become 2 log x equal log x squared. And let me move the log x squared to, or move the 2 log x to the right side, and I will get minus 2 log x equals 0. Okay, let's just factorize this. Log x is log x minus 2. Okay. First, log x is 0. This is when the x is 1. Second, you have log x is 2 and x is 100. Okay, got it? So basically, I'm putting the log inside the quadratic functions. Okay, this is also quadratic, but it's a direct approach. But this is really quadratic functions when you need to uh, factorize to find the in quadratic is roots, right? So you find it's log x is 0, log x is 2 from here, and it's 1 and 100. Okay. So don't forget that every log you have, if you see any not having any base at all, it means it's base of 10. Okay. So when you have the log x 0, so this means it's 10 with the power of 0, it's 1. Okay. And this is 10 with the power of 2, it's 100. Okay, I think one more, and then we can conclude our class and continue some examples tomorrow. Log 5 plus log 7. Okay, see if you can solve this one. Log base 5 x log base 7 and also x log base 25 x. Let me check your answer. Mhm. Mhm. Okay, interesting. Okay, you fine? Mm-hmm. Mm-hmm. Mm, can you stop this? Mm-hmm. Can you solve? Can you solve? No. Good, good. Up until here, it's really, really good. Up until here. Up until here is really good. Here. It's having the same log x, right? You can factorize or not. Mm-hmm. How? Mm-hmm. Oh, yeah. Okay. This is 5 2. It should be y here. If you have log with the base and the base have the squared here, this actually half. Okay. If you have log, for example, if you have squared in the x, it's 2. You get it? So if you have log a b with m n, this is actually n over m log a b. So this is half. Okay, let me give you the answers. Okay, look here. Okay, it's all having the log x 5 7 25, and it's all having log x, right? I can write like this, right? It's the change of base rule. Let me move to one side. Okay, x equals 0. I will factorize log x. And x should be 1, right? So log x should be 0 and x is 1. Okay. Okay, finish. So this numbers doesn't really matter because all the things that make 0 is just log x. So x is 1. Okay. So another thing is this is quite helpful, change of base. Okay, sometimes you can make some complicated log uh, easy to solve. Okay, that's a little bit of some log functions and log equations. Uh, I will give you more tomorrow, and maybe we can go for another chapter tomorrow if we have time. And the quiz will be until the exponent and logarithm. Okay. So functions, numbers, quadratic polynomial, and this one, the exponent and log.